Section 5.2, the definite integral. In 5.1, we determined that the area underneath our curve is exactly equal to the limit as n goes to infinity of the sum as I goes from 1 to n f of xi star times delta x. The restriction that we placed here was that f of x must be continuous and non-negative. We want to move on just a bit. Largely the functions we're going to deal with are going to be continuous until calculus 2 potentially. But in general we're going to be dealing with continuous functions that are not necessarily non-negative. So the definite integral is defined over an interval a to b as the integral from a to b of the limit as n goes to infinity of I to equals 1 to n of f of xi star times delta x, provided that that limit exists. If the limit exists, the function is said to be integrable. It's said to be integrable. Now, our theorem here states that continuous functions are integrable. This does not necessarily mean that all integrable functions are continuous. Not by a long shot. But continuous functions certainly are. Now, we're going to apply that idea of a Riemann integral here in just a second, and so we need these two summation formulas. Specifically, we'll need the second one. Alright, so let's dive into this. Find the area between the curve of the function f of x equals x squared and the x-axis over the interval 0 to 2. Use the graph and area formulas as well as the definition of the Riemann sum. Alright, so first we want to know the area between 0 to 2 from the points x equals 0 to x equals 2 of x squared dx, and this is going to be equal to the limit as n goes to infinity, sum I equals 1 to n of f of xi delta x. Okay, now our delta x in this case is 2 minus 0 over n, so delta x is 2 over n. Now we're going to use that delta x. It's not a constant there. Okay, it changes. Well, it is going to be a fixed width. However, as n increases, that actually get the distance between all of our points will actually get smaller and smaller. All right, so our xi is a plus I delta x. So for us, our a value is 0. So this is 2i over n. That is our xi. That is a generic I value based on what we did before. We went from 0 to 1/2 to 2/2, so that sort of thing. Well, we're going from 0 to 2 over n to 4 over n to 3 over n, etc. Or to 1 over n, etc. Alright, so we'll take that. Now, f of xi, we need to find out what this is. Well, our function is x squared. So this would be our xi squared, but xi is 2i over n squared, making our f of xi equal to 4 over n squared I squared is how I'm going to write that. Here, actually, let's put that in the numerator. Alright, so this will be the limit as n goes to infinity, sum I equals 1 to n, of 4i squared over n squared times our delta x. Delta x was 2 over n. Okay, now being that I is what we want to sum, I'm going to go ahead and factor out a few things. Take out a 8 over n cubed, the sum of I squared, which we know from our formula earlier is equal to n times n plus 1 times 2n plus 1 over 6. Yes. Now we want to know the limit of this. Now I want to go ahead and make the observation that we are going to have a cubic polynomial in our numerator, a cubic in our denominator. So all that's really important is the coefficients here. All right, well, our coefficients are going to be, let me just go ahead and add this in here. We are going to have a 2 in the numerator, so times 8, so that is 16 n cubed plus the rest of our polynomial, and a 6 n cubed in our denominator, so that the limit is 16 over 6, or 8/3. So the area from 0 to 2 underneath the curve x squared is 8/3. All right, now I want to make a note about this integral, this statement here. First off, the notation here actually goes back to the 1700s, and it's attributed to Leibniz, okay, Gottfried Wilhelm Leibniz, and he's considered to be the co-discoverer of calculus along with Isaac Newton. And this elongated s, it's exactly what it is, the integral symbol, the elongated s, stands for summation. Okay, just like the Greek sigma stands for summation. There's one thing. Now we have our boundaries on our interval, a to b, where this is our lower limit of integration, and this is our upper limit of integration. Now we actually have two kinds of limits here. We have our limits of integration here, 0 and 2, and we have our limit as n goes to infinity. Those are two separate things. Two separate things, so keep that straight. Now we have what we call the integrand. That is this section of stuff here, generally our function, our f of x is our integrand. Okay, x is our variable of integration we have here, and this dx actually is the change in x. Very similar to this. Okay, these two, this is a d for delta. And I believe that's all the terminology we can throw out there. Alright, so let's move on to number 2. Use the formula for area of a circle to evaluate the integral from 3 to 6 of the square root of 9 minus x minus 3 squared. Alright, so this equation actually is an upper half circle going from 0 to 6 is this end point, and the middle point of that is 3. So here is the area I am seeking to find. The area from 3 to 6 of that function right there. Now if you notice, this is a semicircle with a radius of 3. We have a radius of 3. Actually what we want is the quarter circle. So the integral of square root of 9 minus x minus 3 squared equals 1/4 pi r squared. In this case our r is 3. So this is 9/4 pi, which is roughly 7.069. So that would be the area. So it pays, certainly, to be able to recognize functions and what the graphs are going to look like from them. Example 3, find the net signed area and the total area between the curve of the function f of x equals 2x over the x-axis over the interval -3 to 3. Use the graph and area formulas. Now for the next few of these, we are going to have very good shapes that are going to fit. Okay, these are actually going to form some triangles. All right. So we'll go ahead and do this. At the point 3 and -3, our function is at -6 and 6 respectively. And the area we want to find is this area. Okay. Now, the area for this, the net signed area, is going to be, notice we actually have some underneath and some above the x-axis. So the area of the one on the right, we're going to call that A1, and that A2. On the right, that is a base of 3, a height of 6 divided by 2, minus the area of A2, which is 3 times 6 over 2. equals 0. So we have a 0 net area. Okay, I think of this as if I begin walking across the room to my right. Let's just say I start here. Here is my 0 position, my equilibrium there. Say I move to my right 3 feet. But I turn back and I walk 6 feet, going in the opposite direction. My net gain is actually negative 3 feet. I've gone 3 feet to the left as a net. Okay. How far have I actually walked? My total distance? Well, that's 9 if I add the two together. So you could think of this as negative 6 feet. And that is 3 minus 6 feet, which is negative 3 feet gain. But if I want to know my net, or my total, then I actually need to deal with only positive values and then add those together. All right, so my total area is the next thing. The total area. That is going to be 3 times 6 over 2 plus 3 times 6 over 2, which will be 18. So my total area is the 18, but my net is 0 because those two actually have the same area. Let's see if we can hammer that out a little bit more. Find the total area of f of x equals x minus 2. So underneath this curve over the interval from 0 to 6. At a value of 0, this function is at negative 2. And at a value of 6, this is at 4. And it's a linear function, so we have something that looks like that. Now the area underneath this is this area plus this area. All right, now the place that it intersects there, if we set this equal to 0, we find that x equals 2. X equals 2. So what this is going to come down to, our total area is the integral from 0 to 2 of x minus 2 dx plus the integral from 2 to 6 of x minus 2 dx. Now to find the total area, what I'm going to do is make both of these positive. So I'm going to take the absolute value of whatever I get out of those area functions. So the first, that is a triangle with a base of 2 and a height of 2. Now because it's below the x-axis, it's going to end up being negative. So 2 times 2 over 2 plus the absolute value of that triangle as a base of 4, height of 4, and dividing that by 2. So that would be an area of positive 2 plus 8, and so my area is 10. All right, we have some properties of the definite integral. If the limits of integration are the same, then the integral is just a line and has no area. So imagine a function here, and I have a value a, and I want to find the area of that line. Well, that line is 0. You could also think of delta x being a minus a over n, which is 0. So the change in x is 0, therefore the volume or the area of my rectangles is going to be 0. All right, the next is if we change the limits of integration. If we go from b to a versus a to b, we are going to have a negative sign in front of our integral. All right, these next several have a whole lot to do with limits. Okay, the limit laws. Because the definite integral is a limit of a Riemann sum. So the sum of the limit of the sums is the sum of the limits. The difference of the limits is the difference of those two functions, but then we apply the limit to it. All right, same idea here with a constant. We can factor a constant out. That doesn't change anything. And this last one probably needs a picture. That if we have, I'm going to draw one case of this. Just take a function, a, b, and c. The value of the integral from a to b, let's switch these two. Okay, let's switch our two limits. I really want b on the end. Alright, so the value of the integral from a to b is equal to the value, the area from a to c, plus the area from c to b. And this will work regardless of what our limits are. Alright, now this actually works when c is between. That's when it just makes sense. But if it's at some other place, it actually works as well. It holds. Alright, use the property of the definite integral to express the definite integral of f of x equals negative 3x cubed plus 2x plus 2 over the interval negative 2 to 1 as the sum of three definite integrals. Sum of f of x dx from negative 2 to 1 is equal to negative 3, there's our constant, integral negative 2 to 1 of x cubed dx plus 2, integral from negative 2 to 1 of x dx plus the integral negative 2 to 1 of 2 dx. Alright, that's all there is for that. So if it's known that the integral from 0 to 8 of f of x dx equals 10, and we know that the integral from 0 to 5 is 5, then what is the area from 5 to 8? Let's actually apply that last part of that theorem, of our rules. The integral from 0 to 8 f of x dx equals, because 5 is between those two, or even if it wasn't, we could make this work. This is integral from 0 to 5 f of x dx plus the integral from 5 to 8 f of x dx. Well, we know that 0 to 8, that is 10. We know that the value from 0 to 5 is 5. And we don't know what that value is. Well, some solving there, some simple solving, algebra there, would tell us that the integral from 5 to 8 f of x dx is 5. Okay, imagine, we don't know what the function is, what it looks like, but 0, 5, 8. Just like in my example, we know this area is 10. We know that this area equals 5, so then that area must also be 5. Next we have the comparison theorem. One specific case, if f of x is greater than or equal to 0 on the interval a to b, then the integral from a to b of f of x dx is greater than or equal to 0. Okay, if there's a positive function, then we're going to have a positive area. That's the way to think about that. Positive f of x, positive area. All right, next, if f of x is greater than or equal to g of x on the interval a to b, then the integral from a to b of f of x is going to be greater than or equal to the integral from a to b of g of x. Again, think of that as a larger function. A function with larger values is going to have area that is larger. Okay, this is actually called the domination theorem as well. That if one function dominates, if it's larger than the other, then the area, the integral, is going to have to also be larger. All right, and then we have our max-min inequality. If f of x is between lowercase m and capital M over our interval, then lowercase m times b minus a is less than that integral, which is less than capital M times b minus a. Here is my example. If I have points A and B, going to box this in. My lowest function value is m. My largest function value is capital M. Alright. So let's suppose I box this in. The area of the lower box, okay, would be m times b minus a. The area of the bigger box would be capital M times b minus a. So certainly the area is between those two. So let's actually apply that one real quick. Compare these two functions. Square root of 1 plus x squared and square root of 1 plus x over the interval 0 to 1. Alright. Well, I would really like to say that one of them is smaller or larger than the other. That would be great. Now, I could look at the graphs, and I'm going to sketch that in just a second. But how I want to start with this is that we know x is less than or equal to 1, and it's greater than or equal to 0. Which means if I multiply by x on all sides, and since x is positive, then my signs stay the same, x squared is less than x, less than or equal to x. Let's add 1 to all sides. So 1 is less than or equal to 1 plus x squared, which is less than or equal to 1 plus x. And then the square root function is a continuous, it's actually monotonic. Can take the square root of all sides. So this is the square root of 1 plus x squared, which is less than or equal to the square root of 1 plus x. I'm going to add one more restriction back here. X is less than or equal to 1. Which means this is less than or equal to 2, which means this is less than or equal to the square root of 2. Okay, so what I can say, based on this statement of fact, is that the integral from 0 to 1 of f of x dx is less than the integral from 0 to 1 of g of x dx. I can also say that the area of both of these is bounded between 1 times 1. Okay, so my lowercase m is 1, and my capital M is the square root of 2. Now, my a and b are 0 and 1 respectively. So I can say that both of these are between, that would be 1 times 1 and the square root of 2. Because our width was 1. So I can actually use the max-min inequality, but what I'm really after here is that the integral, okay, I'm going to go ahead and box that in again. What I'm really after here is to say this, but I can actually apply the max-min inequality to give myself sort of a bound. I have an upper bound and a lower bound. Okay, and that's what these are. A lower bound on my area and an upper bound on my area. All right, one last thing we need to touch on, and that is the average value of a function. The average value of a function is given by f average equals 1 over b minus a times the integral from a to b of f of x dx. So let's find the average value here. What we're doing is we're finding the area and then dividing by our interval. So that should make some sense. So our f average equals 1 over b minus a, in this case we're from 5 to 0, or 0 to 5, times the integral of x plus 1 dx going from 0 to 5. Alright, so at a function value of 0, this is at 1. And an x value of 5, that means we are at 6. So we're actually looking for this area here. Alright, now based on the fact this is made up of a triangle and we have a triangle here in blue, triangle and a rectangle, the area of that is going to be 17.5. So the average value is 3.5. What that means, I'll do that in different color, is if I go to a y value of 3.5 and I make a rectangle here of width 5, going from 0 to 5, the area of that rectangle would be equal to the integral from 0 to 5. So another way to write that formula, we had f average equals 1 over b minus a, integral a to b f of x dx. Another way to write that is that the integral from a to b of f of x dx equals f average times b minus a. So rather than being the lower bound or the upper bound, f average is the exact bound to tell us what the integral is. All right, well, that is the last problem from this section, section 5.2, on definite integrals.